DC&C is the classic. I have found many people adopting gypsum, especially in the transportation area. And of course, I would like to promote the use of Bray and Messina 2019 for shallow crustal earthquakes and Bray Messina Travisero for subduction zone earthquakes. DC&C do tell you to evaluate material strength loss. If it's significant, they say don't use their method. If it's slight, they deliberately say once you have your best estimate of the strength, use a slightly lower strength. Why? Because the model is rigid, perfectly plastic. Soil response is nonlinear, elastoplastic. A way of compensating is to use a rigid, perfectly plastic model that has a strength that's 10% below, so that you can capture times when the stress is high, not high as the strength, but high enough to cause some deformation. That is their way of capturing distributed deformation within the sliding mass. With that strength, they do a slope stability analysis and calculate the yield coefficient, KY. Then they estimate the PGA at the top of the dam or the top of the slope. I have tremendous respect for DC&C, but that's one place where I disagree with them. I have found the hardest thing to do, one of the hardest things to do, is to calculate the acceleration, the one-time peak value at the top of a slope, especially next to a crest. This is showing you some of the range in movement or accelerations you can get depending on the ground motion. With the peak ground acceleration at the top of the slope, which is highly uncertain in my view, they then use that value and then the dimension of the slope, so y divided by h. As the slope gets deeper and deeper and deeper, y over h approaches 1, and you're using an equivalent acceleration, k max, that's a small percentage of the PGA at the top. This is R sub D. It's an incoherence issue, and this looks a lot like the R sub Ds that Professor Kramer talked about yesterday. Now I have uncertainty, however. One reason why I started my work, one of my first consulting projects while I was at Berkeley, I calculated with my flush analysis a Kmax value that was out here. And I thought, Harry Seed can't be wrong. And then I realized these are not bounds. They did one finite element analysis. They had only a couple of ground motions. They primarily did an approximation called a shear slice analysis to develop this. The reality is like the analysis that you saw for R sub D by Andrew Chetin and Ray Seed. There's a lot of uncertainty. There's some waves that are coherent. There's some conditions where the wave response is highly incoherent. So actually, Kmax should vary with the period of the sliding mass. Just like Ray Seed showed that R sub D should be a function of Vs 12 meters. With Ky and Kmax from those previous steps, you come up and then you estimate displacement as a function of magnitude, because magnitude represents duration. The DC&C paper is well worth reading many times, but do not use the figures in the paper. ASCE made a mistake and misset the typeset, and you're off by a factor of 10 if you use the figures in that paper. To cross them off, this figure is correct. Now, the late Professor Harry Seed said, we derive these from a limited number of cases. Professor Bray, Professor Kramer, listen to me, update these as you get more time histories, as you get more results. So that's what I did. I followed his orders. I'm used to doing that, being in the military. I recognize he used very few ground motions. Some of the ground motions he made up because there weren't enough long duration motions at that time. He estimated PGA at the crest to get Kmax. Kmax could be no more certain than the uncertainty of PGA at the crest. They used a very simple analysis because it was difficult to do analysis in the 70s. They did a decoupled analysis. Their bounds are not true bounds. There's no estimate of uncertainty. Gibson came along and did a rigid sliding block analysis. Whenever you see someone estimating displacement as a function of PGA, that means they are doing a rigid block analysis. Because peak ground acceleration is the spectral acceleration at 0 period. Gibson himself states, I have treated the landslide as a rigid, perfectly plastic body. I do not allow the mass to deform internally. Therefore, my model is for thinner landslides in brittle materials. It is not appropriate for deeper landslides in softer materials. When an author tells you not to use their method for certain cases, you should not. His model is only for rigid sliding masses, or when what you're looking at can be approximated as being rigid, having a period of 0. Working with Tony Ugello and then Ellen Rathje and then Thalia Trabuzero, we developed a methodology that then we've now been able to update with Jorge Macedo in 2019, and you have the spreadsheet and the paper that's it's accepted and soon to come out in ASCE with this method. We did a nonlinear soil response. We did a fully coupled deformable stick slip model. Yes, it's one-dimensional, but I want to run a lot of ground motions, so I'm willing to take a simpler model, and I know for base sliding, one-dimensional analysis is reasonable. We can adjust it for topographic effects, and we can talk about that later. I used a range of different TS's and KY's to represent the sliding mass response. We did an upgrade from the 700 ground motions that Thalia used to almost 7,000 two-component motions. We didn't use two components as being independent. Some people have done that. We took the two components, we ran the analysis, and then took the average of those two components to represent a random orientation to that ground motion. We ran both polarities and took the maximum displacement from whatever polarity was worse, because whether the ground motion is like this or the opposite can make a difference. Faye McDeasy, I think, did about a couple dozen analyses to get out of Berkeley with a PhD. Ellen Rathje ran about a few hundred analyses to get out of Berkeley with a PhD. Thalia Trabuzero in 2007 ran almost 60,000 analyses to get out of Berkeley with a PhD. Jorge, to get out of Berkeley with a PhD, ran almost 3 million analyses. So I'm looking for students who are willing to do 1 zillion number of analyses. And then we validated it. It's a two-part model because we realized early on, and I had some discussions with Professor Derek Karajian, who really understands these methods, that when you calculate 1/1000th of a millimeter and 1 millimeter, they are tremendously different mathematically, but as an engineer, they're the same number. 0. Negligible. So we used a mixed random variable approach to first say, well, what's the probability I'm going to get negligible displacement? And we picked less than 0.5 centimeters as being the threshold, in the sense that in most cases you're worried about 5 centimeters or more, so we're an order of magnitude below the deformations that you typically care about. The probability of zero displacement will obviously increase. You're more likely to get zero displacement when the KY increases, because the slope's getting stronger. You're more likely to get displacement, so the probability of zero displacement goes down as the acceleration increases. And then this almost looks like an upside down response spectra. When you get near resonance, you are less likely to get zero displacement, and as you get away from resonance, you're more likely to get zero displacement. So we have a model for that. The equation's in the spreadsheet, it's in the paper. The key is it's a function of KY, spectral acceleration at 1.3 TS and TS, where TS is the site period, the period of the sliding mass. We then looked at calculating the displacement when it was greater than 0.5 centimeters. And of course, displacement is going to reduce as KY increases. It's going to increase as spectral acceleration goes up. It's going to tend to go up as magnitude goes up. There's going to be a little effect of fundamental period. So these are the parameters you have to know to put in the spreadsheet to calculate the non-zero displacement. And because these are two parts of the model, you want to take the probability of calculating zero displacement and then the calculated displacement, given there is a displacement, and combine them to develop what the spreadsheet does develop, log displacement versus yield coefficient. And we're showing you some trends for 0.8 g spectral acceleration for a sliding mass that has a fundamental period of 0.3 seconds, magnitude 7, shallow crustal earthquake. This is what you get on average, and this is the plus sigma and the minus sigma. You'll never say 15.2 centimeters. You'll say 7 to 30 centimeters. You'll always give a range of displacement. Now, of course, displacement increases as acceleration increases, and displacement increases as KY decreases. What's informative is sometimes you and the owner say there's a certain level of displacement, in this case 30 centimeters, where as long as the displacement's less than that, you're okay. If it exceeds 30 centimeters, you're not okay. So you want to be able to do a probability of exceeding a certain threshold. This is for one scenario event, just as an example, a magnitude 7 at 10 kilometer distance. What this shows you, if your KY is 0.2 or 0.3 or 0.4, the chance of exceeding 30 centimeters for this scenario is negligible. Don't waste the client's money getting refinements on KY and the period of the sliding mass, because it doesn't matter. If your KY is 0.05, then you're going to exceed, in all likelihood, 30 centimeters of movement for this scenario. So maybe you shouldn't waste the client's money, you should try to do remediation. If you're in this range, where KY is maybe 0.1 or 0.08, knowing the shear wave velocity, which gives you TS, or knowing the KY, is it actually 0.07 or 0.1 or 0.12, that's where you should invest the money, because that could be the difference between unacceptable or acceptable performance. We looked at this, 10, 15 years ago with Diatrab Zero, and we said there's got to be a difference in the fault normal direction for a pulse motion and fault parallel, because we have time histories like this. This is recorded time history from the Northridge earthquake, where we see a pulse because of forward directivity, which is significantly higher than the ground velocity in the fault parallel direction. In fact, you can see that in this trace. So clearly, the slope should be more likely to move for the fault normal component than the fault parallel component. So if the slope is oriented to where it will move in the fault normal direction, I would think it would move more than if it was oriented at the same distance, same magnitude, but oriented in the fault parallel direction. So we took every ground motion that was a forward directivity pulse motion, as identified by myself or Jack Baker, I think it's 191 pulse motions, and we rotated the two components with vector math to get what the component would be in the 1 degree, 2 degree, 3 degree. Every 1 degree we calculated the time history, and then we ran that time history through our sliding block model and found the orientation that gave us the maximum displacement. And then we found the orientation that gave us the median displacement. And we're going to use the median displacement. Half the values are higher orientations. Half the orientations can calculate a higher displacement. The other half is low. We'll use that for the fault parallel orientation. But for slopes that will move in the fault normal direction, we think it's reasonable and not overly conservative to use the max calculated displacement from that orientation that gives you the maximum displacement. We call that D100. So for a magnitude 7, period of the sliding mass equal to 0.5 seconds, PGA is 0.58, and the peak ground velocity is 99 centimeters per second. This is what you get in the fault normal direction. This is what you get in the fault parallel. So my orientation is, if you are within 45 degrees of the fault normal direction, you use D100. If your slope orientation that will move is within 45 degrees plus or minus of the fault parallel direction, you can use the D50. We had to add peak ground velocity in this model because it's so important for pulse motions. You're not going to use the method. I wouldn't use the method unless it's been validated. It's shown for more cases in the paper. Just bringing out a couple of points. Here's some landfills that were shaken by the Loma Prieta earthquake. This is what was observed. This is what we calculate. We say it's pretty likely to not get displacement. If you do get displacement, it's small. That's consistent. For dams, 2 dams, Austrian Dam, Lexington Dam, especially, both of them were shaken by near-fault pulse motions. This is what was observed, 50 centimeters of shear-induced deformation for Austrian Dam, 15 centimeters for Lexington Dam, and the chance of zero displacement is 0, so it's negligible. And I'm going to get displacement, and these are the displacement ranges from 16th percentile to 84th percentile, and you can see it captures those values. If you look closely, you'll find that there's one of these cases. Where is it? Here, this is the one. Well, we're a little bit too high. I want to be honest with you this time now and show you that I'm mainly good, but not always good. Here's an example, 57-meter high earth dam, located 15 kilometers from the magnitude 7.5 earthquake. This is an actual dam that I'm using, and I'm essentially saying that that's the failure plane. There's no liquefaction. The soils are not going to undergo significant strength loss. Did a total stress analysis because it's going to be an undrained loading during an earthquake. Got a CU of 14 kPa and a FEU of 21 degrees. Put that into this program, calculated the K. That got a factor of safety of 1. The yield coefficient is 0.14. This is a triangular block, so I'm using 2.6 H over VS, where I averaged the VS like I talked about on the first day, to get 0.33 seconds. So I have my KY, 0.14. TS is 0.33. I know it's a magnitude 7.5, a distance of 10 kilometers. I use 1.3 times TS to represent my degraded period. So the degraded period of the sliding mass is estimated to be 0.43. I use ground motion models for outcropping rock below the sliding mass. So this is the sliding mass. So what I'm saying is, if that was removed, what would be the ground motion for this foundation below here? Just like when you do a building, you basically do the ground motion based on the site. You don't do the ground motion at the top of the building. Don't take the ground motion at the top of the slope. What you care about is the forcing function. You care about if this was outcropping, what would be the acceleration, spectral acceleration at the period of the sliding mass, and that's what you're using as the forcing function. We got a PGA, a spectral acceleration of 0.45 g, a peak ground velocity of 52 centimeters per second. The probability of zero displacement, plugging it into these equations, is low. That shouldn't shock anyone. The non-zero median displacement, used with epsilon equal to 0, ends up being 7 centimeters. The standard error term is around 0.7 on a natural log scale, so that's almost a factor of 2. So you can do it precisely, or you can just say it's about half to 2 times the median estimate. So in this case, it's 3 to 14 centimeters, which for most well-built dams is fine. Don't do the calculations on your own because there's a little nuance that I'd say half the people miss. Use the spreadsheet that I give you. Well, that was shallow crustal earthquakes. I gave a series of talks in Peru about 4 or 5 years ago, and I recognized they were using Bray and Trapezero in subduction zones. And I was worried about that, so I got with Jorge and said, let's develop a subduction zone database, and let's do our method for subduction zone earthquakes. So this is through the kindness, Pierre did share some ground motions. Kishida helped us, Bob Dara, Julian Bomber shared some ground motions. So we were able to cobble through and get over 2,000 interface megathrust earthquake records. If you go through the whole process, you'll end up with a simplified model that I won't go through that estimates seismic displacement as a function of yield coefficient, and you can see the importance of magnitude. Magnitude 9, all things being equal, is going to generate a lot more displacement than the magnitude 7 because of the duration. This is just confirmation that we're estimating displacements that are consistent for the most part with these cases. Well, that's the way we normally do it. We get the spectral acceleration, given a magnitude and distance and an epsilon. 50th percentile is 0 epsilon, 84th percentile is +1. And then we calculate our displacement based on those. Can we do better than that? Well, people have started saying, well, I'm not going to use the deterministic spectral acceleration. I'll use the hazard curve to calculate it. That's kind of a pseudo-probabilistic. If you want to really do a full probabilistic, which I'm calling the performance-based method, why not compute the displacement hazard curve? Because here's a case, for example, where the annual rate of exceedance and spectral acceleration are the same at this return period. But you can tell that if you're integrating the hazard over different return periods, this is probably more dangerous than this case. So instead of using spectral acceleration from a hazard curve, why don't we integrate that with the model and directly calculate a mean seismic slope displacement hazard curve? I'm not the first person to suggest this. And now we're looking at a hazard curve that directly is giving you the performance measure that you want, displacement. Professor Macedo actually developed some software that's available at his website that's downloadable that allows you to do these calculations relatively easy. It looks complicated, but it's actually just a lot of calculations in a spreadsheet that as long as the spreadsheets are organized, it's not that difficult. One of the good things about it too is if you do a probabilistic analysis, you don't have to say your slope has a KY of 0.105. You can admit it could be 0.100, it could be 0.11, it could be 0.12. And so you can put a logic tree and give different weights. In this case, it gives you different weights to magnitudes. And now you're going to get all of the uncertainty because of the displacement given the ground motion, but then also all of the uncertainty given to you not knowing what the Ky is or what the Ts is. If you do a de-aggregation on spectral acceleration at this return period, you would say the shallow crustal earthquake is most important. Develop a suite of ground motions from that event. But if you look at it in terms of displacement, for the same scenario, you would say no, it's the interface subduction zone earthquake that's actually governing the hazard. So you can actually misinterpret the hazard if you focus on spectral acceleration as opposed to focusing on calculated seismic displacement. Because you can deal with uncertainty, you realize if my Ky is low, regardless if I have no uncertainty, which is the black line, if I have some uncertainty, these are the coefficient of variation of Ky and Ts, or a large uncertainty, it doesn't matter. The slope is so weak, you're going to get large displacements, and variations of Ky and Ts don't matter. However, if you come down here to where it's stronger for this case, there is a difference between the high uncertainty case and the lower uncertainty case. So again, probabilistic methods, since you've done literally hundreds of thousands of deterministic analysis, you can then mine that data and gain insight. Let's go back to the fact that a lot of people do not like to calculate seismic slope displacement. I have given up trying to defeat the pseudostatic slope stability analysis. I have declared defeat, and now I'm going to want you to do this analysis, but I want you to pick that K, that special K. I'm getting hungry for breakfast now. I want you to pick that K appropriately. Now, logically, K should depend on the level of shaking. No debate on that. Magnitude, distance. But it also should depend on the dynamic response of the dam or the sliding mass. But K should also depend on the criticality of the structure and what you consider to be the acceptable level of performance, which is how much is the allowable seismic displacement. Some structural engineers have told me you're building on top of a slope. If the slope moves 5 centimeters, they're nervous. Other owners and structural engineers have told me that building with that mat will not have an issue if you have 30 centimeters of movement. So the owner and the architect, in discussion with you, make the most important decision of saying, given the structure and its criticality and the consequences of poor performance, what is the acceptable level of displacement? 5, 15, 30 centimeters. Well, how do you develop this estimate of K? Well, we have a model based on 3 million analyses that calculate displacement based on K and a bunch of other parameters. Let's just flip it around. Let's calculate K as a function of the allowable displacement, the seismic demand based on spectral acceleration, the period of the system, the magnitude, and what you consider to be the acceptable level of uncertainty, the epsilon. These are the equations, which you don't have to worry about because they're in the spreadsheet. Let's take a scenario. Let's take a magnitude 7. Forget about the magnitude 6 right now. Magnitude 7 earthquake. The period of the sliding mass, you've estimated with 4H or VS and some shear wave velocity measurements to be about 0.3 seconds. Not that big a deal if it's 0.2 or 0.4. You'll notice that it's not that sensitive to TS. So I picked the period of the sliding mass. I have the magnitude of the earthquake. And I know the spectral acceleration at the degraded period of the sliding mass. These are the calculations at different acceptable levels of displacement. So let's go forward. If the spectral acceleration at my hazard level or my deterministic analysis at the period of the degraded slope period was 1g, then if I could accept 5 centimeters of movement, I would use a ky of 0.34. But if I could accept 15 centimeters of movement, I would accept a k of 0.19. If I could accept 50 centimeters of movement, I would accept a k of 0.08. The lower the k, the more displacement I'm accepting. So k is a function of allowable displacement. To pick a k that's not a function of displacement means you don't care about performance. You don't care if it moves 5 centimeters, 15 centimeters, or 50 centimeters. Of course, as the acceleration goes down, the k goes down, and as the acceleration goes up, the k goes up. It's higher for a magnitude 7 than it is for a magnitude 6. So this is the procedure that's spelled out in the paper. Of course, you look at material strength loss. You use reduced strengths if you think that's appropriate. Use strain-compatible dynamic strengths. If you're calculating a meter of movement, you have to have a strength that's compatible with that. You and the owner have the difficult decision. Step 2 is the hardest decision, but it's the right decision. You have to decide what's allowable, and you have to accept. You have to say what's your acceptance of exceeding it. I got 50-50. You can use epsilon to 0. Okay, I want to make sure there's only a 16% chance that I'm wrong, then using epsilon to 0.74. You estimate the initial period of the sliding mass. You characterize the seismic demand, and you put those parameters in the spreadsheet, and you calculate your K. Then you perform a pseudostatic analysis with that K, and if your factor of safety is greater than 1.000, then your displacement, if you had done a displacement-based analysis, will be less than what you judge to be allowable. Do not use a factor of safety greater than 1.1. Factor of safety is highly nonlinear, and as the factor of safety changes, the reliability of the slope changes dramatically. I've tuned this to a factor of safety of 1.0 deliberately to remove that nonlinearity. So it's mainly about severe strength loss. If you don't have severe strength loss, calculated seismic displacement is a way to gain insight. This procedure does what everyone does, uses the yield coefficient. Shaking is not PGA, but it's better to be the spectral acceleration at the degraded period of the sliding mass, as well as magnitude and PGD when there's pulses. It does admit that the sliding mass is not rigid, and it does a coupled seismic displacement analysis. It's been developed for shallow crustal earthquakes and subduction zones. In the end, once you pick the allowable level of displacement, the most important thing is the earthquake and the material characterization. The calculation of the displacement is the least important thing. By Jorge doing 3 million analyses, he's done that part for you. And so you can use the simplified method as the final estimate for many cases, or as the first step when you're trying to do an advanced analysis. And if you want to lean back on the pseudostatic analysis, now I think you have a scientifically justifiable, rational way to select that K, not just based on some value, but based on the ground motion and what you consider to be allowable displacement. Thank you. Any questions?
Currently, SAE, which spectra do you use? You want in the rock, you want with FA, or which one?
The best way to get the spectral acceleration at the degraded period of the sliding mass is using something like a ground motion model or a code for the site conditions below the mass. So if it's rock, you would just use the spectral acceleration at the period of the sliding mass For the rock condition, if it was actually a C site under your sliding mast, then you could use FA and FB to bring the spectrum up for site, and then pick the period of the sliding mast, pick the spectral acceleration that lines up with it.
Because usually you take the height of the slope, and with that you calculate the period,
Yes.
and then with the material of the slope, you calculate the spectrum. Is that right?
Yes. So we're estimating seismic demand with this method the same way a structural engineer estimates seismic demand for a pushover analysis of your structure.
Okay, with the material and the slope.
The material below the slope.
Below the slope,
But below the slope,
sometimes you don't know. Only
Well-
know you know the material in the slope.
well, you have, the material below the slope is important. If it's rock, if it's C site or D site, that changes the input to the slope. So you have to spend some effort to characterize the material below the slope.
Not easy.
Right? But it's important. So now what you could do is you could do various variations of what's below the slope and find out if it's important.
But including a cognitive.
There's a paper I can show you where we simplified this and used the spectral acceleration at 0.2 seconds for very stiff slopes. In Canada, they had a lot of slopes that had periods of about 0.1 to 0.3 seconds. So I adjusted it to come up with the spectral acceleration in the short period range and used that as the demand parameter. So maybe that's a simplification you want to make to put it into the code. I can give you the paper on that.
Okay, I think